Carla is parallelograms, wondering if there are as many special properties for parallelograms as there are for triangles. He remembers that it is possible to create a base that looks like a parallelogram, a rotating a triangle about the midpoint of one of its sides.
Cool, thank you. So we're not gonna use tracing paper, it's just interest of time. I'm just gonna just draw it for you. So if I were to get, literally get tracing paper and draw a midpoint here and rotate this triangle along its midpoint, it would look something kind of like this. So that's the original. And I'll switch colors to do the rotated one.
Where's my name? Where's the name on my test?
It'll look kind of like this. So again, if you rotated this triangle, and it's kind of hard to visualize, but if you rotate it about its midpoint, 180, it should look like the green triangle. Does that kind of make sense if you kind of visualize it? I know it's a little hard to visualize sometimes in this way. Faith, go ahead. I'm only focusing on this side here.
Yeah, well,
Well, sure, yeah, you can rotate any way you like. Sure, it's up to you. Yeah. Um, no, not necessarily. No, I just seem like an easier one to see, I guess. But so the answer is yes for part B. Yes, it truly is a parallelogram, and that's because alternate interior angles are congruent. So that would verify it. Now, what else can the congruent triangles tell you about a parallelogram? There's a few things it could tell you. So if you use CPCTC, we know the opposite sides are congruent. Also, the opposite sides are parallel. Also, opposite angles are congruent. When you have all that happening, you have a parallelogram. A parallelogram is just simply a four-sided object with two pairs of parallel sides and congruent sides. That's what a parallelogram is. And CPCTC helps us because, well, yeah, of course these are the same, right? Or of course these are the same. Or these are the same. And if you have alternate angles congruent, then these are parallel. Or these are parallel. We got all this going on here. Okay. So questions on A, B, or C? A, again, we rotated. B, we answered the question. Yes, it is. C, we're using CPCTC to conclude that these other sides and angles have to be the same, which is true for all parallelograms. So for part D, says, does this work for all parallelograms? The answer is yes, it does. Can I move the screen? I'll actually freeze for a moment. Actually, we'll do it right now. Okay, so this works for all parallelograms. That is, does the diagonal of a parallelogram always split the shape into two congruent triangles? So the answer is yes, and we're going to prove it. Knowing only that the opposite parallelograms are parallel, create proof to show that triangles are congruent. Great. Okay, let's do it. So for number one, we're going to say AD is parallel to BC. And at the same time, I'm going to say AB is parallel to DC. And that's given. Now we know BD equals BD. That's always a free point in some ways. That's reflexive. And for number 3, see, if AD is parallel to BC, I know these angles are the same. And what's the reason for that again?
Alternate
Yep, you guys got it. We've done it a few times already. Alternate interior angles congruent for parallel lines. And that's not the only pair. I mean, yes, angle ADB congruent to angle CBD. And also switch colors because AB is parallel to DC. Those are the same as well. So angle CD or angle ABD, ABD is congruent to angle CDB. So that's also true. Now that you have a side that's the same,
Sure, you can do angle A and C too.
not yet. We're not ready to say that yet. Because we're only focused on parallel lines. So because you don't have a line going through angle A and angle C. You have to have a transversal. Like imagine these were extended and you draw a line like that. That's what you're looking at. Or if I extended these two and drew a line, that's what I'm looking at.
How do you prove that a angle A?
We're gonna do it in a moment. But no, we can't. We have to use a CPCTC afterwards.
Oh, like there's.
Well, so now I can prove triangles are congruent, right? Triangle ADB is congruent to triangle CBD. And that's ASA. Now, if you want to go further and say, oh, is angle A the same as angle C? Yes, you can say that. That's a CPCTC. Or AB is equal to CD, CPCTC. Or AD equals BC, CPCTC. Then you could say, and that what makes them true. So, you guys got your proof?
What?
Are you guys
Like.
Yeah.
okay? I don't even I don't know.
Similar but on the test, and then so we were like kind of like checking our answers
Okay,
with this
okay,
one. And then,
okay. By the way, there were multiple versions of the quiz, just so you know. So every pair got a different. So that's why I'll go over the answers when I grade them. So, but if you want me to look at your quizzes during class, that's where I finish. I could do that. It's fine. Okay, we got two more examples, but both multiple parts, and then we're done with the notes. This quick, and then you guys could work on the homework, which are just more proofs. So Kip is confused. He put his two triangles from problem 749 together as shown at the right, but he did not get a parallelogram. Okay. What shape? Sure, yeah. Okay. What was that? Sorry. Okay. What shape did he get instead? So instead of rotating like the way we suggested in the previous problem, he did it a little differently, but that's okay. So what do you think this kind of looks like? Yeah, it's a kite. Yeah, it's a kite. And that's because you have two pairs of congruent sides that are adjacent. So that's adjacent to this. And that is adjacent to that. Okay. Next two. So you're saying adjacent to Colette. You're saying that adjacent to William, right? So just next two. That's all. So what transformation did Kip use to form his shape? It looks like that was a reflection. Rotation. Yeah, I don't want to think about that. Could be that's a little complicated, but it could be a reflection. What do the congruent triangles tell you about the angles of the shape? Um, well, what we do know is that yeah, so here's what you could say. You have one pair of congruent angles. Let me label it because it's being a little bit busy here. A, B, C, and D. So angle A is congruent to angle C. And yeah, B and D are different, so we can't really say anything about that. So yeah. So but angle B not the same as angle D. So okay.
Where? Oh.
Yeah, just by looking at it. So but BD bisects. We could observe this also, angle B and angle D. So we're just observing. That's all we're doing right now. We're observing what's happening here. So it's just more conceptual. That's what we're talking about today. So again, you get a kite if you reflect the triangle along one of the sides. And yeah, you get just one pair of congruent angles. Angle A is congruent to angle C. B and D are not, but the side BD or the diagonal BD bisects angles B and D. So cool. Good. All right, let's keep going. 752. Here we go. So kites. Kip shared his findings with his kite and his teammates. Okay. Carla, who wants to learn more about diagonals of a kite. Carla quickly sketched the kite at the right onto her paper with the diagonal showing the two congruent triangles. Nah, we don't need to do that. Add the other diagonal. Okay. Also for you guys right here. And fold the paper in different ways. Write a conjecture based. I'm not sure what they want for this one. Discuss how diagonals may be related. Oh, I got it. Okay. Actually, yeah, what do you think is happening here? Got it. Okay, now I got it. So let me label this. I know what they're getting at. How is AC comparing to BD? And I want to take a stab as the relationship between AB, segment AC and segment BD. Yeah, they're perpendicular. Yep. Yep. The diagonals are perpendicular. 100%. Right. Also, it seems that BD bisects AC. So AC gets cut in half. We're gonna prove it actually. We're gonna do it right now. Yeah, we're gonna prove it right now. It is. Yep. So we're gonna do a proof here. So prove when she drew the second diagonal, Carla noticed that four new triangles appeared, right? If any of these triangles are congruent, then that may be able to help us prove our conjecture from part B. Okay, the perpendicular part. Examine triangle ABC below. Are triangles ACD and BCD congruent? The answer is yes. And it's going to be about hypotenuse. So the answer to your question, Faith, it's going to be about hypotenuse Lake theorem. Actually, no, I take it back. It's going to be by side angle side.
Of the original.
Yeah, because here's what's happening. I already know.
Oh, they're like some SF.
It's perpendicular.
Correct. We know AC is congruent to BC. And angle ACD. Oh, because we did that earlier from because remember we took the same triangle, we flipped it. Right? We took the same triangle and we created a second triangle. It's from up above. Oh, I label it differently. Here. Let me label consistently over here. My apologies. Yeah, I did it wrong over here. That should be AB and CD. My apologies. So what we did was we took the triangle up above. Oh, it's gonna be really hard. I took this triangle and I reflected it. That's why I know these are already the same.
Okay.
I already know that.
Yeah.
And I already know these not cut in half. We're not cut in half. I already know these are the same. So I reflected it.
Yeah.
I already know that.
Like, I should know that.
This one's something.
Like, that it is the bisector. Like.
Because by CPCTC afterwards. But let me finish proving this. So angle ACD is the same as angle BCD. I know this also. So since I know that, and CD is going to the CD by reflexive, then I have enough to say these triangles are congruent by SAS. Then I have enough to say that. So once I have that, then these two angles, angle ADC and BDC, have to be the same. And because they form a linear pair, they'll have to be vertical right angles.
No, right.
Because they're right next to each other and they're the same.
Yeah, so.
So they both have to be 90. That's really why.
So, but if you have like two right angles right next to each other, does that mean it's automatically?
It's a perpendicular bisector. Actually, because it's perpendicular for sure because of the right angle. And it's bisect because these are also the same too. So it has to cut in half. It's both. Well, perpendicular bisector actually takes care of all of it. It's cutting in half and it's perpendicular. It's doing two things at once. Yeah, so I already know that ADC is the same as DBC because I deliberately flipped the same triangle along one of the sides. So I know they're the same. So that's what's happening there. So all this is telling us that, hey, because of the triangle stuff we know that these diagonals are going to be perpendicular as well as one of them cutting the other one in half. So I kind of already answered part D already because it asked us to prove all this and I already proved it. I mean, there's a more formal way of proving it, but I think given that you guys have been at this doing school for a long day today, we'll stop there. We have about 8 more minutes. So is it 2:35 we get out? Yeah. So anyhow, I'm all done for today. Just we understood about kites. We understood a little more about parallelograms. We'll talk more about this. This is a long unit. So if you're still kind of grasping, don't worry about it. We're going to talk more about it. I know you guys are focused on the quiz and other stuff. Homework is going to be that single sheet that I put in front of you. Yeah. It's 7 proofs. It's just more practice on proofs.
Oh.
I don't have an answer key for it yet. I'll make one when I get a chance. And these should be pretty short proofs. So anyhow. And that's all. We're all done for today.